hope you guys are having a good day. This video is going to be very similar to the last video I made as far as content goes. About half of it will be the same. And the second half of it, when we talk about the net change theorem, that's going to be applications of this definite integral that we can use. And there's a lot of them. Just forewarning you, there's a lot of them. We won't spend a lot of time on very many of them, but there's a lot. So first of all, I want to discuss what an indefinite integral is. Just a slight change that we're going to have. Hopefully you can kind of look at this slide and see what that slight change is going to be. Now, there's not going to be any upper and lower limits on my integration. Okay? But as you can see, everything else is still going to be the same. So I'm still going to be looking at taking the antiderivative, come over here. So that means the relationship between capital F and little f is that if I take the derivative of capital F, it should get me back to little f. And all my same rules are going to be the same. So I'm still just going to raise the exponent by 1 and then put it over the new exponent. I like to do the 1/3 as a fraction out in front. Okay. One slight change, though. Remember that little pesky plus c that we had a few weeks back? It's wanting to come in. Now, let me explain why on this. Because the reason that is because, remember, if I take the derivative of, say, 1/3 x cubed plus 2, the derivative of this is going to be, we'll drop the 3 down in front and multiply. It's hard to go backwards now. But yeah, that's going to be 1. It's going to be x squared, and the derivative of 2 is 0. And if I was to do, say, the derivative of 1/3 x cubed plus, let's do a negative 1. Let's do negative 100. It's still going to give me x squared. So in other words, if I take the derivative of 1/3 x cubed plus any number, it's going to give me x squared. And that's what I need to show on this, since I don't have a specific numbers right here that I'm integrating in between. Okay. So here is a table of everything that we have taken the derivative of. Therefore, it's fair game for us to integrate anything on this table. So let's try something. I'm wanting to integrate this guy. Ooh. Okay. Well, now we could go through here and do all of my shortcuts on this. Okay, so I could sit here and pull the 10 out. I could take the integral of each item and not ready for the secret yet. I could take the integral of each item and pull its constants out in front, if that helps. It doesn't really help me a lot, because I'm still going to be taking this 10 right here, bringing it down, and raising the exponent by 1, putting it over the new exponent. Don't raise the exponent by 1, put over the new exponent on the secant squared, okay? If you're having trouble, go back to slide, look and see what I took the derivative in order to get secant squared. And you should find it to be tangent. And once I take that and those two integrals, I'm going to have that plus c tacked on the back. Now, go ahead and simplify this. Tell me 10 divided by 2, or 10 divided by 5 is 2. And this would be full credit. So I think it's a little bit less work when I have an indefinite integral. Right? And SEMO, on their final, I'm going to tell you, is going to hit harder on the indefinite integrals, and because they're a little bit easier to grade going down and make sure that you know all of your stuff. Okay, so I could probably do that in way less steps, and I probably won't divvy up those integrals anymore. So however many steps you need to show to get to this answer. Trig wants to come in and play. All right. Now, might need to rewrite this. We have to rewrite this right now. Hopefully, we might get a better way of working this in the next video as far as a more straightforward approach. But I just want to break stuff apart, right? I like stuff written out. So I see I have the cosine theta on top, and just playing with it, I see I'm left with a cosine over sine, which that will give me a cosine theta. This isn't really helping. I messed up somewhere. Let's go back and try that again. Like, what is going on? Tony, it's actually calculus time whenever I'm making this video right now. So without you guys here, it was a little bit harder for me to wake up. I'm gonna break apart this sine on bottom because I don't have that many cosines to divvy up. All right, that looks a little bit better right there. Now I'm looking back at my slide a couple slides ago, and I don't have anything that looks like this, but I do have some trig identities floating around right here. Cosecant theta, cotangent theta. That was in there. Now, I almost have this on that slide. The problem is that they have a negative in front right here, don't they? And mine is positive. Well, if I just make it so my antiderivative is negative, it should work out. Okay. So if the derivative of positive cosecant is negative cosecant cotangent, then the derivative of negative cosecant has to be positive cosecant cotangent. And that would be my correct answer. Now, this book's kind of weird. They don't stick to these indefinite intervals very long. They fall back in love with the definite intervals. And so we'll go back and do a couple of these to warm us up for the net change theorem. Okay. So remember on these, the only difference we're going to have, now I've got it in this polynomial form. I love the polynomial form because I just raise the exponent by 1 and then put it over the new exponent. See, I raise the exponent by 1, and I have an x squared. 6 divided by 2 is 3. Now, on this one, remember, I don't need the plus c. So I want you to see the difference, because this is going to be the back half of your test coming up. It's going to be just nothing but a bunch of integrals, and some are going to be definite, some are going to be indefinite. You need to know the difference between how to work them. So if I plug in 3 in for all this, let's see, that's going to give me like 81 over 4. And then if I plug in 3 right there, it's going to give me 27. And if I plug in 0 in for both of these, I'll just show you, I'm going to get 0 and 0. So plugging that in my calculator, I get negative 6.75. Again, that negative just means that I have more area underneath the curve, underneath the x-axis than I do above the x-axis. All right, I'm going to let you guys try one. Hit pause on the video, give this one a go, and then you can come back and see what I did. Awesome. Did you catch that tangent inverse in there? I hope so. And then I've got to rely on my calculator. Tangent inverse of 2 right here. Not going to be a nice value, and it's going to make everything decimal out. We saw something like this on the last test, and I wasn't very impressed with how most of you attacked it. So let's talk about this again in case we see it on the upcoming test. And so whenever I go to solve this, I cannot have it as this giant quotient yet. We're not ready for it yet. We're getting close, but we're still about a week away from being able to tackle something that looks like this. And then it's only going to be a very special case when we tackle something like this. Okay, so I need to, this is, again, another one, I need to rewrite the interval. Okay, I need it to match, I need it to either be a polynomial, something I can just take each exponent, raise it by 1, put it over the new exponent, or something that's on my table, like that cosecant cotangent was. So this t squared is a common denominator, I'm going to send it with all these numerators right here on top. And so it's going to divide each one of them, just leaving me with 2 right there. Just leaving me with the square root of t. And leaving me with 1 over t squared. A little dt out there. This already looks better. I'm going to spend one more step making it look even better. And notice I haven't integrated anything yet. Don't integrate until you're ready to integrate everything. So I know I could integrate this too right now, but I'm not. I'm going to integrate everything on one step and get rid of my integral sign whenever I do so. So I think that it's going to be easier to integrate this square root of t if it says t to the 1/2. And I think it's going to be easier to integrate this 1 over t squared if it says t to the -2. I feel better about that. So that's just going to save me a little bit of headache, a little bit of mental math if I can get it written like that on my sheet of paper. So now I'm ready to integrate. So raise the exponent by 1. That'd be t to the 1st power over 1, still 2. Raise the exponent by 1. That'd be t to the 3/2 divided by 3/2. Well, dividing by 3/2 is the same as multiplying by its reciprocal. And it always throws people off right here. Let's raise the exponent by 1. That would be t to the -1st. And then put it over the new exponent. That's going to be a -1 combined with the -1 in front right here. That's just going to change it to a +1. And I'm looking at evaluating that from 0. What is it? Oh, no, 1 to 9 this time. Now, if you want to spend a step going back and putting everything back in square roots and 1 over t, that's perfectly fine. I'm not going to. Okay, instead, I'm just going to try to do some mental math here. I plug in 9, gives me 18. If you don't trust me on any of this, go ahead and type everything in your calculator and see if you get the same thing. And so I plug in the 9 for this t right here. That's going to be the square root of 9, 3. 3 cubed is 27. 2/3 of 27. Well, that also gives me 18. And then 9 to the -1st, that's just the reciprocal of 9, 1/9. Now, I didn't look out here because now I have a 1 as my lower limit of integration. So whenever I subtract off, I'm going to have to plug in 1 in for everything. And I'm going to use parentheses on that to show that I'm subtracting everything from the function whenever I plug 1 in. But plugging in 1 shouldn't be too bad. It's going to give me 2/3, and 1 over 1, which is 1. But all that's going to be subtracted off. Whenever I type this in my calculator, I got a 32-point repeating 4, which is the same thing as 32 and 4/9. I'll accept either one on that. So that would be my answer. Big kicker on this. Hopefully the integration part is still not throwing you off from here down. Oh, not from there down. From here down. The kicker on this is getting it to this form right here. And there's going to be some in the homework again that I'm going to assign that you just need to practice this, because this stuff, like derivatives, in case you didn't believe me for derivatives, if they weren't going to go away, this integration stuff, if you're moving on in calculus, it definitely isn't going away. You're going to see it a lot. So let's talk about some applications of this. Now, I might go kind of fast through some of these because we don't really need them all, but you'll be able to come back and read the slides on the video if I don't touch on everything. Okay? And so the application of this, the main one that they use is just a net change theorem, and that's going to just kind of encompass everything that I'm going to talk about as far as applications go. And so we said that the integral of a rate of change is simply the net change. It's the net change of whatever the antiderivative is evaluated at b minus whatever the antiderivative is evaluated at a. Now, we've been doing this all along. It's just we're used to working it where I took the derivative, and what does the derivative tell me? If I took the derivative of the position function, what did it tell me? Well, it told me velocity. Now, as we're going to see here in a minute, I'm going to be giving you the velocity, and I want you to go back and tell me what that means with the position function. And so you can see it's just still going to be an antiderivative. Right here, this V prime right here, it says it stands for the rate at which water flows into a reservoir. If I was to integrate whatever this rate is right here, it would actually tell me the volume of the reservoir in this time interval that goes from T1 to T2. So that's one application of it. We're about to see a lot. Right? Let's see, I don't even remember who did the chemistry ones. I remember it was good, but if C of T is the concentration of a product, then they said that the rate of reaction is the derivative. So now, if I'm given the rate of reaction between two times, T1 and T2, I can now integrate that, use this whole net change theorem, and it would go back and tell me the change in the concentration of the two chemicals in that same time interval. I don't remember who did physics either, but I remember it was good as well. And they did the linear density rod, and they said that this rod had different density throughout the rod. And now, and they called it rho. And so now, if I know what rho is, I know what that linear density is, I can now work the problem backwards, and I can tell you what the change in the mass of that rod is between those 2 points on the rod, A and B. Population growth. All right. If the rate of growth of a population, so if I know what the rate of population growth is, I can tell you how many people there is between two different time intervals. Right? I can tell you the net change in the population. The cost of producing a commodity. Again, some of you guys did this as a presentation back in the second quarter. And you said that the marginal cost, we were able to find the marginal cost of something. Well, if I integrate that, I can now tell you the net change in cost between maybe, I think it was making 1,000 bolts of fabric and 1,001 bolts of fabric. Or I might spread it apart a little bit. I might say I can find the net change in cost between making 1,000 bolts of fabric and 2,000 bolts of fabric by just using this integration technique that we've been talking about. All right, this is the one I want to hit on a little bit. All right, so if I know what the velocity is, I already said that I can integrate it, take the antiderivative, and it will tell me its displacement right here. Okay. Now, the big thing, it tells me displacement during that time period. Okay. So it doesn't matter if the object's moving in a positive direction, negative direction. By the time I integrate it, I'm going to be able to tell you its displacement and how far it has moved away from its initial spot. All right, not the distance it traveled, but by the time it went forward and backward and forward and backward, forward and backward, if it went that many times, how far it moved from its initial spot. If I'm wanting to know the distance between it, I've got to do a little bit of math with it, all right? I've got to use this absolute value of v, and that's going to tell me the total distance traveled. And I'm going to work an example with that here in just a minute. But the idea is, just graphically so you can see it, if I'm given a velocity function, like I am given right here, the displacement is going to be this area, and then I'm going to subtract off the area that's below the curve, and I'm going to add this area up here, because it's above the curve. And that's going to tell me how far it has moved from its original spot. Whereas if I'm wanting distance, the difference is going to be is that this negative distance, or this negative area that I have down here underneath the x-axis, I have to change that to be positive. And we've talked about that a little bit. It was one of my properties of integration, properties of integrals. So I'll go back and refresh you on that with maybe this example. Nope, got to talk about acceleration. So in the same way, acceleration, if I was to integrate acceleration, it would just tell me the net change in velocity between two different times. I told you there was a lot of them. I don't know if you believe me or not, but now you do. So we have this particle that's moving along a line so that its velocity at time t is this. Okay. I want to find the displacement of it. Okay. So there's a difference on this between part A and part B. And you'll probably see this on the upcoming test, knowing this difference right here. And so if I'm wanting to know its displacement, that means I'm wanting to know wherever it was at S of 4 minus wherever it was at S of 1. And so to do that, I can just integrate from 1 to 4 my velocity function. It's t squared minus t minus 6. And it's in great respect to t, so I'll say dt. Don't have much room right here, and I'm going to use that part B down there. I'm going to need more room down there. So I'm just simply going to work this horizontally. I'm going to raise the exponent by 1, put it over the new exponent. Raise the exponent by 1, put it over the new exponent. Raise the exponent by 1, and evaluate it from 1 to 4. And so, let's see. I'm going to plug in 4 in for all this. I'm going to have to, I'll just come up here. Change color so we can follow it. When I plug in 4 in for all this, ooh, what is that? 4 cubed is 64, I think. I do the math in my head on a video. I know 4 squared is 8, or 4 squared is 16, half of it's 8, and then 24. And then I'm going to subtract off. I'm going to plug in 1 in for everything. I like plugging in 1 because all I got to do is bring coefficients out. So all in all, whenever I do this, I got negative 9 halves. What would that be? This displacement meters. Is this in meters? Measured in meters per second. So yeah, this would be meters. So this particle has moved 4.5 meters in a negative direction. So it could be 4.5 meters to the left, or it could be 4.5 meters down, whichever way the negative direction is. It doesn't specify in this one. Now, suppose I want to find the distance traveled during this time period. That's going to be a little bit harder, okay? And so, first thing I want to do, if I'm going to do distance traveled, is I'm going to take my function. I'm going to write it correctly. It's still early, guys. I'm struggling this morning. And I'm going to factor it. I'm going to get some critical numbers from it. I'm going to get t equals 3 and t equals negative 2. So what that means is that at 3 and negative 2, something critical is happening right there. Probably the particle has the potential to change directions right there. Well, negative 2 is not in this time interval right here. So that's going to be just some extra stuff that I don't need. But what I need to do is, the difference on this one is that whenever I integrate from 1 to 4, I'm going to put the absolute value signs around my velocity. I'm wanting to make it so this guy, that it's always moving in a positive direction. So whether I'm going forwards or whether I'm going backwards, it's calculating a positive direction. If I was to go to Cape Girardeau and then come back, my displacement would be 0. But if I was to go to Cape Girardeau and then come back, my distance traveled would be, I don't know what that is, 100 miles, something like that. Okay, so I need to figure out which way it's going and where. So I'm going to have to break this apart as the integral from 1 to 3, it's moving a certain direction. And then I'm going to have to do the integral from 3 to 4. Got that 4 from right here. It's moving a certain direction, okay, with respect to time. I didn't leave myself enough room right there. But what I'm going to do is I'm just going to make it so that my velocity has to be positive. So from 1 to 3, I'm going to choose a nice number that's between 1 and 3. I'm going to choose 2. Seems like a nice number. If I plug 2 in for my velocity, that's going to give me 4 minus 2, that's 2, minus 6, negative 4. So it's moving in a negative direction right here. So whenever I take the, whenever I integrate this, I'm going to want to use a negative v of t to make it so it turns around and turns positive. So what I hope that means is between 3 and 4, that I'm moving in a positive direction. And if I plug in 3.5, if I plug in 3.5 in for these t's right here, or if you plug in 4, it doesn't matter, it's going to give me something positive. So in this case, I want to leave it so it's positive. Okay, so let's plug in our stuff right here. So let's go back to red. So I'm going to integrate from 1 to 3, negative v of t. Okay, well that's going to be negative t squared. So I'm just going to change the signs to do some way. Negative t squared plus t plus 6. And I'm going to add that to the integral from 3 to 4. Well, I've just got v of t here, so all of that's going to be the same. It's just going to be t squared minus t minus 6. Okay, so I've got this big old thing to integrate right here. Keep moving further to the left, so I'm going to need more and more room. So I got negative 1/3 t cubed. See, we're just raising the exponent by 1, throwing it over the new exponent. That's a 2 right there. I'm crazy with it. So this part of the problem, I'm wanting to evaluate from 1 to 3. And now I'll make it so whenever I was moving in this negative direction, it'll count positive for me. Okay? Plus, and then all this is the same as it is above, so I'll just copy it down. 1/3 t cubed minus 1/2 t squared minus 6t. But this time it's being evaluated from 3 to 4. I am running low on room down here. Right. Final line, because I don't have any more room. I could just take the answer and just say, trust me, that's the answer. But I'm not. Let's see, 3 cubed is 27, negative 27, over 9, over 3. Let's call it 9. And then I got 3 squared over 2, that's 9 halves. Or 4.5, that's what we call it. We're going to decimal that anyway. If you want to do a decimal right here, that's good. Now I got to go back and plug in 1. So that's going to be a negative 1/3. Now notice I'm not subtracting off all. Oh, I am subtracting off all this. Now it's a fiasco. Subtracting off all this. So minus a negative 1/3 minus a positive 1/2 minus a positive 6. This may end up being subtracted off. So that's the first half. I'm going to color coordinate it in case you have questions on this later. This plus sign's coming straight down right here. Hopefully I have enough room. 4 cubed. 4 times 4 is 16. Oh, man. It's awfully early in the morning. 64 over 3. Something like that. And then 4 squared. 16 divided by 2 is 8. 4. It's negative 24. Getting all these negatives in here, it's going to be hard to believe my answer is going to be positive. But it will be. It will be. Now, plugging in 3, I should get some similar numbers. Now, I'm plugging in 3, so I've got to subtract off what I get whenever I plug in 3. So it's still going to give me 3 cubed divided by 3. That's going to be 9. And then it's going to be 3 squared is 9, so there's negative 9 halves. And negative 18. That's good, because that negative is going to distribute through, and it'll turn out a lot of those will be positive. I just typed all this in my calculator, and I got 10.17. So 10.17 meters is how far it traveled, is the distance that it traveled. Okay, counting all the positive and negative directions that it traveled as being positive. So big difference between those two answers there. Okay. One more problem I wanted you to see. This is the power consumption in the city of San Francisco for just a random day in September. P is measured in megawatts, T is measured in hours starting at midnight. So like this would be how much power is being used at 12 o'clock noon on a random day in September. I want to estimate the energy used that day. Now, I don't think this is one that I talked about, okay? But actually, my power and my energy used, they're going to be related such that if I take the derivative of the energy used, it gives me power. So I'm wanting to know, whenever we work a problem like this, is I'm wanting to know the area underneath this curve, all for the whole day, from 0 to 24 hours. From 0 to 24 hours, doing the power. Well, that's just going to be that's just the derivative of the energy. Okay. Which we know is just going to be the energy used, the net change in energy used from 24 hours to 0 hours. Now, they don't give me a nice function to integrate on this one. So I'm going to have to go old school on this. You're going to have to draw rectangles. Right? And so I'm going to try to use like midpoints. I think the book on this one uses interval widths of 2, and I get 12 numbers going across. They've already got it set up so nice. I'm gonna cut out a little bit of work and do intervals of 3. Okay, so intervals of 3. That's going to be at 1.5 on each one. So right here, and I'm just going to do my old Riemann sum here and do length times width of each one. Pretty good rectangle right there. All right, I'll look back at some of my old ones and they were rough. And so I'm just going to do this all the way through right here. Use even less energy right here at 4:30 a.m. Some people are waking up at 7:30 or way up here. And then by 10:30, everybody's computer's up and running. They got their coffee making done. And at 1:30 right here, they're just acting like they're working. Right? So we're taking naps. Got the earbuds in by now. And then lost track of time. Started using this army time on me. This had to be 16, so 2:30. Not sure. You kind of see what I'm doing on this, and I know this is taking a while. But hopefully it'll be a good shortcut for me. Just everybody went to bed. Everybody's coming back down. And sure enough, where we started right here, hopefully we pick it up super close to it. Over here on this side, we do. So, if I'm looking at doing this, I'm going to be able to approximate this by just doing length times width of each one. I'm going to go ahead and do my shortcut. I'm going to go ahead and pull out my width from each one. Okay, factor out the 3 that they all have in common. Okay, so now I just need to find how much power is being used on this first one right here. This is just going to be an estimate, guys, so don't get caught up on trying to match the back of the book on this. 4 to 5, 400, 415. My notes aren't of any use right now because I use 2 subintervals on it. Or not 2 subintervals, a width of 12 subintervals. All right, this next one right here, it's a little less, barely above 400, maybe like 405. And then from 6 to 9, everybody's waking up, 660. And then from 9 to 12, that height is going to be 6, 7, 8, 820. Uh-oh, lost count where I was. Maybe I should put check mark on. 1, 2, 3, 4. 1, 2, 3, 4. All right. I'm going a little bit higher on this one. 8. Oh, that looks pretty close to the middle. Maybe a little bit shy of the middle. 8:45. Oh, there we go. All right. So the next one came back down, still above 8. Not much above 8. 8:15. And again, these are just estimates. A little bit below 7, maybe like 695. I'll check one. I'll count them in a minute. 1, 2, 3, 4, 5, 80. Obviously, I hope you see that these are just kind of estimates for me. So let's say I had 24 hours a day. I've used 3 for my widths, so I should have 8. 1, 2, 3, 4, 5, 6, 7. Good. And so now I just get the opportunity to type all this in my calculator. 415 plus 405 plus 660 plus 820 plus 845, 815. This is an awesome video, just listening to me list off numbers like this. 15705. Really close to what I got when I did 2 subunits. 15,705. Let's see. This is my energy. So this has to be measured in megawatt hours because I'm multiplying. Yeah, megawatt hours. That's how much energy got used in San Francisco on that random day in September. You're going to be able to sleep better at night knowing that now. So, here's the last assignment I want to give before the upcoming test. So, not a lot of new stuff going on in this video. We just have to really practice on that distance travel. I think that's going to be the hard part. Other than that, we have a lot more integrals in this assignment, both definite and indefinite, so make sure you know the difference between them. Any questions on this, have them ready for me during the Q&A or next time you see me.